that the electron itself is not moving. So be very careful about this, that the electric charge is not moving. That is the premise of this chapter, because the next chapter that we're going to do is current electricity, that the current or the electron is basically going to move through the conductor. Over here, the electron or the charge is not moving, it's stationary on its own position. So that is a distinction between the two chapters, and we're going to explore basically what we're looking at is the electric field established by these charges. So first, let's look at what is a charge and what it looks like. So we have two types of charges. The first one is positive and the second one is negative. One thing that the students generally don't understand about this point is that being positive does not mean that it does not have or it doesn't have any negative charge. It does have some negative charge, but that is less in number in comparison to the positive charge. So it's all about dominance in terms of quantity. Whichever charge is greater on that specific charge, we'll consider that to be that charge. For example, if this is a positive charge, we can assume or we can say that the positive charges in number will be greater than the negative charges in number. For example, it's possible that inside this charged body there are 10 positive charges and there are 7 negative charges. So it has an excess of plus 3 charges. So overall, we assume that this is a positive charge. Similarly, over here, the negative charge would simply mean that the negative charges in terms of quantity are more in number in terms of positive charges. It's not possible that this will have entirely negative charges or this will have entirely positive charges. It's not going to be that way. Another misconception over here would be that if we have an object that has no charge is technically not a preferred term. We prefer to write down a neutral. Why do we say that? Because when an object represents no charge or a neutral charge, that means that the positives and the negatives are equal in number, overall cancelling each other's effect out. Hence, there is no dominance or there is no extra charge available on that sphere or on that charge. So it's all about the quantity. It's not about pure presence of a positive or a negative or no charge. Do we understand this point? Yes or no? All right. All right. So the next point that we have is charging or charging by friction. So you may have done this experiment in your younger ages, that when you rub a plastic ruler on top of your head in your hair and then you try to pick something up with that, a piece of paper or a very light object, so you may notice that it is generally attracted towards that. Have you experienced that? So that is purely because of static electricity. So how is that happening and what's basically happening? So in your course, it's not your job to figure out whether this is going to end up becoming a positive charge or it's going to end up becoming a negatively charged object. What you're supposed to know or describe is that after friction, if something is being rubbed and they have the capacity to exchange electrons, one of the objects will end up becoming positive and one of them will end up becoming negative. So for example, the most common example given in your book and in almost every literature regarding this chapter is that, for example, we have a plastic ruler and we have a piece of cotton cloth. What we're going to do now is going to rub them together, and after rubbing them, friction is going to cause both of these objects to become charged. And how is that going to happen? We're going to discuss that later. So after rubbing them together, we find that one of the objects is now positively charged and one of them is negatively charged. Again, remembering which one will become positive and negative is not your course. What you're supposed to remember, what you're supposed to describe is how one of them is going to become positive and how one of them is going to become negative. This is the question given by the examiner. He's going to set up the situation for you. He's going to tell you himself that after rubbing, due to friction, one of the object could be any object. Object A has become positive or negative and object B has become the vice versa, right? So then he is going to ask you, describe the process, how this may have happened or how this may have taken place. So what you, for this case particularly, how you're going to write this down is that electrons moved from rod to the piece of cloth by gaining thermal energy or by gaining simple energy due to friction. Simple as that. Now notice, have we described it that the positive charges moved? No. Always remember that only the electrons will move from one object to the other. The positive charges do not leave their position. And there is a reason for that, we'll get to that later. So electrons moved from the rod to the cloth by gaining energy due to friction. So previously what would have happened is that this is a neutral object, so positive and negative charges would have been equal in number, equal in quantity. Similarly over here, they would have been equal in number in terms of positive and negative. What we have done by friction is that we have given these electrons some energy, thermal energy, and they have moved from this rod to the cloth. Now what has happened is that there is now an excess of negative charges, which now is going to, of course, going back to the same concept that an object is negatively charged, considered negatively charged because it has more positive, and positive is considered positively charged because it has more positive, or you can say it has an abundance of positive charges in quantity in terms of, or in versus the negative charges. So over here we can see that now negative charges are high in number in the cloth, and there are less negative charges on the rod because they have now traveled to the cloth or the piece of cloth. So that is how these two objects end up becoming charged. And again, I am enforcing this point again and again, that positive charges do not move from their position, only the electrons move from their position. And the reason for that is every substance or every object that you see around you that you can hold, that is solid in nature, be that water, be that gas, be that the solid object itself, the table, the wood, the laptop, every single thing around you, that is made out of the atoms, right? So for example, if this is an object that is in front of us, it is made out of a fixed positive nucleus and of course an orbiting electron, like this. Fixed positive charged nucleus and an electronic orbit, like this, so on and so forth. So what we're doing right now is we are only extracting, or we are only discussing that these electrons may move out of this object. So when they do, they leave behind these fixed positive charges. And the solid object that you're touching right now, or any solid object that you're touching right now, the matter itself, or the tangible matter itself, is basically this nucleus. This is what you're trying to touch. But you never come in contact with these charges. And that's very interesting. That's of course not a part of this chapter, that's a bit higher physics. Everything that you're touching right now, you can never come in contact with that object virtually. You are touching them, but you're never going to be in contact with them. Why? Because the positive charge of a nucleus and the positively charged nucleus of your hand, of your own hand, they are going to repel each other, and there is always going to be a certain barrier between you and the object, right? So that is just an interesting tidbit that you can explore further if you want to. So we do see that we are touching the objects, but that is just because of the Newton's third law. You see, when you're trying to push together these two positive charges, they're exerting a force on each other for repulsion. So the sense of touch that you're feeling right now is basically the Newton's third law repulsion, you can say in one way, right? So you can explore this further, but the thing, again, coming back to the point, the tangible, solid, liquid, gas, whatever you're feeling right now, that is the positive charge. The matter itself is that positive charged nucleus. Electrons are not important for this discussion. So electrons can move from one object to the other, but the positive charges will not move. That's why when you rub the plastic ruler on your head, you still feel that it's solid. Despite the fact that it's now positively charged, you still feel the solid, because the solid is made out of the atoms itself, not the electrons, right? The electrons are now on the other object that they're trying to attract. So always justify, yeah.
So, and say, like, for example, this rod was made of just one element, if the protons somehow move, they would just lobby that element anymore. So,
Yeah,
which we can't erase. But
yeah, yeah. So always justify your answer in terms of movement of the electrons. Always. That's how you're going to answer your question, right? Okay.
mm-hmm.
So that's why you will notice that over here I've written down the electrons move from the rod to the cloth. For example, if he had asked me that why the cloth has become negative, then I would simply have written down electrons have moved from the rod to the cloth. Now they are more in number on the cloth, overall giving it an excess negative charge, and they have gained energy from friction. Simple as that. So whatever you justify, either the abundance or either the lack of electrons, you're going to justify it by the movement of electrons, not the positive charge. Positive charges do not move. Sometimes what students write down is that positive charges have moved on the rod from the cloth. This is entirely wrong. This is wrong physics to begin with, right? Okay, so the next idea or the next topic, this is what we've done for charging by friction. Then we have electric field. So in electric field, we have to assume that this is a positive charge and this is a negative charge. What is the electric field going to look like? So it's exactly like how the gravitational field looks like, but the only difference is that the gravitational field is always attractive, but the electric field can be sometimes repulsive and sometimes attractive. So the field lines will be radial. They will be actually pointing out 90 degrees to the surface like this. 90 to the surface like this, and I'm using a word radial. You will see this word in A-level physics as well. So what does that mean? It means that the lines are perpendicular to the charge itself and they are straight lines. They are not curved, right? So positive charge, the field lines are pointing outwards, and for a negative charge, the field lines, again, they are radial, but they will be pointing inwards. So they are pointing inwards like this. And again, they are going to make an angle of 90 degrees at the surface like this. So so the question over here is that how did they figure out that the direction of the positive charge is supposed to, or the electric field of the positive charge is supposed to be pointing outwards, and for the negative charge supposed to be pointing inwards? The concept or the idea is known as test positive charge. So this is a charge that is extremely small in terms of these individual charges. It does not exist, it's negligible. So, but it does have a charge, and that is positive. So when we say it's negligible, it means that it cannot have repulsion, it cannot have certain force or such a high enough force that is good enough to repel or attract or disturb the first charge in the first place, right? So it's just a charge, or it's just a testing element that we're going to place close to that respective charge and see what's going to happen. So when we place this test positive charge close to a positive charge, of course they're going to repel each other because they are like charges. So that is why, since this positive charge is repelling the test positive charge, we have drawn this magnetic or this electric field to be pointing outwards. Similarly, if we place this test positive charge close to the negative charge, it attracts it, which is why these electric field lines are pointing inwards. Again, this point is going to be carried towards A levels. That how did we draw these electric field lines? Same idea is applied for gravitational field. How do we draw and why do we draw gravitational field lines always pointing inwards? We know that the gravity is attractive, so just for the sake of testing, we bring in a test positive, we bring in a test mass close to a gravitational field object or close to an object that exerts gravitational field and see what's going to happen. So this object is going to attract this mass, and gravity is always attractive, so this is why the gravitational field is going to be pointing like this always. So this concept of test positive charge, test mass, and so on and so forth, it is just a method by scientists devised in this way that if I don't know what this charge is, it doesn't matter. I don't know. Right now we're working on the premise that we know that this is a positive charge and we know this is a negative charge. If I don't know what this charge is, how will I figure this out? So they have just devised this method. They could have used the negative charge. I agree with the students as well on this part. They could have used the negative charge, but then again, the normal consensus is to use the positive charge. It's fine. So bringing in a positive charge, if this charge repels it, then I can say that this will be positive charge, and if this one attracts it, I can say this is a negative charge, and then I can draw the respective electric field. So that's the only concept, or that's the only idea for test positive charge, or having a test positive charge in the first place. Okay, so now we have to draw electric field between two charges. Let's say that this is a positive charge and this is a negative charge. They're close to each other, or they're placed close to each other in a close vicinity. So the electric field between them is going to be in this way. So from positive to negative, the rest of the field is going to be radial again. And again, in their own zones, in their own places, they're going to be pointing with the respective direction again. So the positive charge is going to point outwards and the negative charge is going to point inwards. And no matter what perspective you look at it from, let's say if we analyze it from this place, if I only look at the positive charge, the positive charge is pointing outwards. Okay, fine. If I look at it from the negative charge, it's pointing inwards. Okay, fine. So it is also satisfying this condition of positive and negative charges, that for positive it should be outwards and for the negative it should be inwards. Any problems up to this point?
No.
Alright, so we have to look at two unlike charges. Let's say this is a positive charge and this is another positive charge. The electric field between them is going to go like this. They will not interact with each other, and there will be a space between them that is going to remain empty, or that will show that there is no interaction of electric field between them. And sometimes the examiner actually asks you to mark the position where there is no electric field. So we generally mark that as this position, that is over here, as X. So this is the area where there is no electric field. And if you had placed a test positive or test negative charge at this place, it would not have experienced any force whatsoever. Right? Okay. So now we move on towards the parallel plates. How we're going to look at the electric field of parallel plates. Now previously what they did was, there was one concept associated with that, but now it's not. So positively charged rod and negatively charged rod are parallel plates. This concept will be carried into A levels in terms of capacitors, so keep that in mind. So we have from positive to negative straight electric field lines like this, and of course we need to represent the arrows from positive to negative. One thing that was a part of your course but now it's not anymore is the end effect. Basically two electric field lines in the curved manner around the plates. These were a part of your course but now they are not. So this is how we're going to look at them. Right? Do you understand this point? Okay, and how can they do that? Is by simply connecting two plates with a simple battery. So keep that in mind. So we have negative and positively charged. A simple battery or a simple cell connected to two plates will cause one of them to be positively charged, one of them to be negatively charged. And this is how the electric field is going to be between them. This is the electric field direction. Right? Okay, so one last concept, that is coulombs, and we're going to work with that in the next chapter as well. So what is coulombs? How do we look at this coulombs? So basically when we talk about charges, or when we talk about transmission of charges, be that positive or negative, not positive but the negative charges, when we talk about their movement and their relative motion from one point to another, since it's an electron, it's very difficult to count every one of them because they are going to be so high in number that it becomes mathematically impossible, or you can say it becomes mathematically inconvenient to count all of them. So what we have done, we have created a term that is coulomb. Basically this is just a packet of electrons, a quantifiable number, a packet of electrons, just to make things easy for us, just to make counting of those electrons easy for us. So how we look at this is that 1 coulomb is basically equal to 6.25 into 10 raised to power 18 electrons, a fixed number of electrons. So if half of the electrons are moving from one point to another, we will say that the charge is 0.5 coulombs. So if twice as many electrons are moving from one point to another, we will say that the charge is 2 coulombs. So instead of manipulating this number to represent motion of charges, we're going to manipulate this number, as it's a smaller number and it's easier for us to do that. Do we understand that point? Right?
Yeah.
Okay, so, and of course the counteractive is also true. If somebody asks you that what is the charge on one electron, so that would be 1.6 into 10 raised to the power minus 19 coulombs. This is known as the elementary charge, or the charge contribution by just one electron. Of course, this is being found by cross multiplication, right? So, but we're not interested in that. Okay, so this is how we look at coulombs. That is a packet of electrons, and basically made for our own convenience for the mathematical calculation. That's all, right? Okay, so let's talk about the flow of charges. What if they were moving? How would I quantify that? How would we put a number on that? So flow of charges is known as electric current. This is basically from the next chapter, but that the part is included in this one. So I'm going to start a bit of that over here, and then I'm going to carry that to the next chapter. Okay. So flow of charges, or the flow of electrons, that is the electric current. So how do we look at this? So for example, this is a conductor, a piece of wire, and the electrons are moving in a certain direction. But why are they moving in a certain direction? Now this concept is very important. We will find this concept as EMF in the next chapter, that is electromotive force. The force that motivates the electrons to move in the first place, right? Because previously what would have happened, if the conductor is just randomly placed at any place where there is no battery in it, the electrons would be moving randomly throughout the structure like any other atom, like any other particle. But when you provide it with a certain battery, for example, or a certain voltage, they will start moving in a certain direction. And why is that happening? Is because of the battery, there is a negative charge over here on this side of the conductor, and there is a positive charge on this side of the conductor. Most likely they behave like two parallel plates, like the way we have done before, the electric field between two parallel plates. So that is how a conductor behaves. So when the electron is actually placed between these two plates, or you can say these two ends, it is not only being repelled by the negative plate, it is also being attracted by the positive plate. So that is why the electron starts moving in a certain direction. And that eventually comes to be known as electromotive force provided by the cell or the battery. Right? So the concept actually comes from this point, why the electron starts moving in the first place. This is why it starts moving. Okay, so when the electrons are moving in a certain direction and there is a cross-sectional area for this, let's say there is a certain cross-sectional area through which the electrons are moving, and they're moving through this cross-sectional area in a certain time t. I will quantify this as electric current in such a manner that I will say that this is the rate of flow of charges through an area, or through a cross-sectional area per unit time, because when we say rate, it is including that word as well. So how do we make the formula out of this? We're going to say that current I is equal to charge, which is of course the packet of electrons. If I go back, charge is represented in coulombs, and the symbol for that is Q, and the SI unit is coulombs. So how many packet of electrons are going to move through that cross-sectional area per given unit time? So effectively, this is how many number of electrons are passing through that area in a certain amount of time. Do we understand up to this point?
Yeah.
All right. So that is the end of this chapter. We are going to move to the